Okay, so second order kinetics is our theme. It's the second part of the calculations. We will look into zero order at the end, but I'm not going to spend much time talking about the zero order. So for second order kinetics, you're going to have some chemical turning into products. Not writing a full equation. Second order kinetics that we're about to study is not two chemicals that are both first order. So the second order kinetics we're talking about is one chemical A, and the rate law is second order for that one particular thing. Okay? You might think that if something is first order for two chemicals, you could use the same math, and it's not correct. It doesn't work. So what we're doing only works when the rate law is K times concentration of one chemical squared. Second order overall. Okay. Looking at our units, the rate is typically in concentration per time. So it doesn't have to be, it could be in pressure per time, but if we're using concentration, we're going to have moles per liter per second. Our concentration squared factor is going to be moles per liter squared. So to make the units work, the rate constant is going to have an inverse concentration to cancel out one of the m's in our concentration factor, and it's going to have inverse seconds to get the seconds part of the rate. So that's going to be one set of units. We want to look at things graphically. And what is the time concentration relationship? Okay. So we don't get a natural logarithmic relationship when you, as you do in first order, you get an inverse relationship. Okay. 1 over the concentration at some future time is equal to a rate constant times time plus 1 over the original. So we're not going into the derivation of the science of where these relationships come from. If you're curious, any textbook will go through where these come from, but where these time versus concentration relationships come from involves calculus to get these relationships. So until you finish studying calculus, it's probably not worth going through the proof or the reason where these come from. This is already in a y equals mx plus b form. So time is going to be our x variable. So I'll label things as I label them on the equation. Our slope, which is what's multiplied by our manipulated variable, is going to be just k. So we're going to get a straight line with a positive slope. When we looked at first order kinetics, negative k was the slope, but now we have positive k as the slope. Okay. In order to get this, what we need to plot on the y-axis is not the concentration, but the inverse of the concentration. Okay. We had to plot the natural log of the concentration for first order kinetics. Last, we've got this term. This would be our, B value. I just wrote a wrong letter. That is M. I wrote everything right on my graph. I just put the wrong letter. So our slope M is K, our intercept B value. So 1 over the original concentration is where you would start at time equals 0. So one thing we'll look at towards the end of this lesson is if you take some experimental data and you graph it, you can figure out your order. If you get a straight line when you do the inverse of the concentration as your responding variable, you'll get a straight line if it's second order. If it's first order, you have to take the natural log of your concentration data in order to get a straight line. So you can kind of graph your data two ways and see which one gives you a linear relationship, and you can figure out your order. I'm just going to do one math problem. You could solve potentially for the concentration, okay? You could solve for the time, or potentially solve for the K value. If you knew an initial concentration, a final, and how long it took to get there, you could get the K. So I'm just going to solve for one of these, and the rest you'll figure out and get used to in your homework. So our 1 second order kinetics example. So this reaction follows. Second order kinetics, we're given a rate constant, so that's our K value. We're given an initial concentration, and we're asked to calculate the concentration after 22 seconds. So first order kinetic, we have to realize that's the inverse relationship. You are given your first and second order kinetic equations on the formula sheet, but they're not labeled. You have to know when to use the natural log relationship and when to use the inverse. So I'll go through the math fairly quickly. This is not tricky algebra. The natural log was a little bit more tricky in the previous first order kinetic lesson. So the heart of this question is calculate the concentration after 22 seconds. So that is our concentration at some later time. Instead of writing subscript T, I'm going to go after 22 seconds. So that's what we're after. Our K value. Inverse concentration, inverse seconds. I'm just writing the units a little differently to help show how they cancel. 22 seconds. I don't have to worry about any time conversion. Watch the questions in minutes and hours that you convert them to seconds, or you match whatever time is in your K value. Units wise, we're all set. Seconds over seconds cancel, so we're just going to get 1 over concentration in both of our terms. So the first term comes out to 17.60 inverse concentration. The second term so we just need to add these up and then do one more step. Just be careful, we're not done. We have the inverse of our answer. So if we take the inverse of both sides, we'll flip from 1 over the answer to our answer, and we're done. So the concentration, okay, I've been just going A sub T. You could go T or A subscript 22 seconds. Okay, now we're at our final answer, so I'm going to round down to 2 significant figures. Okay. And both the numerical value gets inversed and our units get inversed. Okay. So we've got that concentration. Okay. So our next topic will be half-life. So we get a very different outcome with half-life in second-order kinetics. Typically, the formula we're going to get to for half-life is not on your AP formula sheet. So I don't expect there to be AP mathematical questions in half-life, but I want to talk about the theory and the outcome. There's something very different than first-order kinetics. So I have our relationship for second-order kinetics up. For figuring out the time for half the concentration, what we need to do mathematically is get rid of our future concentration, and that is going to be 1/2 of whatever the original concentration is. So that's the substitution I'm going to do. That is pretty much the exact meaning of half-life, half the concentration originally. Okay. The rest of this is going to stay the same. So now I'm just going to collect our original concentrations and solve for T. I'm getting rid of that inverse half, which is just 2. And then I'm going to do a second algebraic step. I'm going to take this plus 1 over A concentration originally and move it to the other side, so we get minus. That simplifies to just the inverse of the concentration originally equals KT. I'm just going to go back, add a subscript. This is the point where I turn that T into the T1/2. It's not any time, it's only the half-life time. So for second order kinetics, the half-life is 1 over the original concentration times the rate constant. Before, in first order kinetics, T1/2 equaled just a function of the rate constant, which meant that the half-life was constant. Here we have a concentration factoring into our half-lives. So the half-lives are not constant. They vary depending on the original concentration. Okay. So let's look at this graphically. What does it mean for thinking about half-lives for second order kinetics? This is going to be a sketch. Let's say we have concentration starting at 1 unit. It doesn't matter what the units are. I'll label the midway point. I'll cut that in half again, a quarter. So for second order kinetics, a half-life would be going from 1 and dropping down to 0.5. Okay. And let's just say that took 10 seconds to drop. Now if we wanted to calculate the next half-life, you've got to redo the math at this point. You have to go 1 over the concentration times the K value. Even though the formula says the original concentration, it's not necessarily at the start of the reaction, it's at the start of the half-life. So the second half-life is starting here. What happens to this ratio when we put in a smaller denominator? We're going to get a bigger fraction. The whole thing is going to be bigger. So the second half-life is going to be bigger. In terms of time, would say that's longer. First order kinetics, this wasn't true. So the time it's going to take to go from 0.5 down to a quarter, again, I'm just making up relative numbers. This might now be 12 seconds. So the first we had 10, now it's 12. I'm not saying it's always 20%. These are just relative numbers. If we wanted to look at a third half-life, it's going to be even longer still. So second order kinetics is getting slower and slower and slower, or even much slower than first order kinetics, which has this constant halving. Okay. So for advanced placement, the math is something you probably won't do, but the concept is something you should have and know the difference between first order. First order half-lives is right on your formula sheet, so that's something you could be asked to calculate. So we're through most of the theory of second order kinetics. In a previous video and lesson, we covered first order kinetics. Let's take a really quick, brief look at zero order kinetics, and then we'll wrap everything up. So zero order kinetics, the rate is equal to K times the concentration of one of our reactants, but it's going to be to the 0 power. So that's going to be just 1. So the relationship of the concentration of A with respect to time is, it's just going to decay by the rate constant times time, okay, starting at whatever that original concentration is. Okay. So the K is just going to determine how fast the concentration drops. So we don't have a natural log relationship like we had in first order. We don't have that inverse relationship like we did in second order. It's just a straight up linear, straight decay. It's the only time that you can plot the concentration as your responding variable, and you're going to get a straight line. Time is going to be our x, our slope is minus k, and our intercept is b. So you should be aware of the y value to get a linear relationship in zero, first, and second order. Time versus concentration. We're going to start at just straight up the original concentration, and we're just going to have a negative slope, so it's going downwards. So it's going to go straight down. So it doesn't matter what the concentration is, it's just going to decay. Now you might get something like this happening if you just have a solid surface that's driving the reaction, and that solid surface isn't changing at all. Its concentration isn't going down. So a catalyst is driving the reaction, and you just get a straight constant drop, okay? Because something is not changing, okay? Again, solid surfaces would be a typical thing that may not change. So that's really the end of kinetics, first order, second order, third order. We're going to look at determining the order graphically. Okay. So we have some information, we have a reaction, we have some data, and I didn't write out the question, but it's kind of in the heading. We want to determine the order graphically. Is this first order, second order, third order? And just looking at it, it's going to be very difficult to figure out what the order is. Is this dropping straight, okay? Or do we have to take the natural log or inverse to figure out whether we get a linear relationship? So here's our straight up data. If time versus the straight up concentration is linear, then we'd have zero order. Okay. In order to get a linear relationship for a first order reaction, we would get a straight line if we plotted the natural log of the concentration. If this is second order, would have to plot 1 over the concentration in order to get a straight line. So it's a bit time consuming to figure out the order graphically. So first part, okay, we've already got the straight up concentration, okay. take your natural log. This might tell us whether it's first, and this would tell us possibly whether it's second, the inverse. Okay. When you do that for all three potential orders, this is the straight up concentration versus time. Okay. If this was, if the reaction was zero order, we would get a straight line with a slope of K. And we do not have a straight line when you plot concentration versus time. So that data is not zero order. Here's our potential first order, natural log versus time. This is our first order test. Here we would have a slope equal to minus K, and the slope would be straight. It's almost looking straight, but it's not quite. There is some curve to it, so that data is not first order kinetics. Okay. Here's our second order test where it's the inverse concentration versus time, and this is where we got a straight line. Okay. And here the slope is equal to K. Here I missed for zero order, it's minus K. So minus K, and then K. And this is what we have, a nice straight line with a positive slope. So that data, which just by inspection, I'm assuming nobody's looking at that and going, aha, that's second order. Okay, you really need to do the mathematical calculations and plotting. Okay, to figure out both something about the kinetics, the K value, and its order. So from the graphical version, we know the rate law now. The rate is equal to K times the concentration squared. Okay. From the graph, you can solve for the K value and have a good understanding of the kinetics of this reaction and make further predictions if you wanted to. So that's something I'm definitely going to want you to practice, and you should practice before an exam. Some of your graphing skills are time-consuming questions, but it's definitely something you want to be comfortable with. Last, this is from the Edvantage workbook. It's on page 59, and it's a really nice summary of all the kinetics. So maybe before you start practicing, or if you're kind of getting stuck and you're in the middle of homework, it goes through zero order, what all the units are, the graphical version when you have a linear relationship, first order, second order, and then it gives you the pattern for nth order, whether it was 4 or 5 or 6 or 10. I wouldn't go too deep into the nth order, but you should really be comfortable with the first and the second order. That's likely to dominate your questions on assessments and quizzes. Okay. So the questions in the Edvantage workbook, they all work fairly well, but I'm going to highlight page 60, 2 to 8, and then after 8 are some big graphical questions. I'd like you to do at least number 11, but if you wanted to do more of the graphical ones, that would be encouraged.